Hey Cap 2 class, this is Mr. Blevins. We'll go over your first discussion forum. So you were coming up with where did these crazy formulas, these crazy integrals come from for these two. So we'll start with the disk method. So the volume formula you should have found here for this is a right circular cylinder. These disks are right circular cylinder, meaning there's a circle on the bottom, perpendicular edge, meaning we're coming off 90 degrees from this circle up and hitting the other circle. So this was a right circular cylinder. It's volume you should have come up with, volume formula you should have come up with, which is pi r. This is squared. This is not a minus sign, and this is h. Okay, so that's what we should have come up with. Pi is pi no matter what. R. Now where's r coming from? This red line. Well, that's this red line, and it's coming off the x-axis right here. So this red line is given by the function. In this case, it was the square root function. And some of you wrote the square root here for r instead of just the function in general. I was hoping you would go with the more generic, just any function, but some of you used square root, and the squaring of the square root gave you just x, and so a lot of you had pi x. And then h right here is given by this distance, and this distance, as we increase the number of segments, we would decrease this distance. This was just delta x. Alright, so h was delta x, and so if I erase that in there, I get the volume of one of these boxes. And then if we take the sum of all of these over a general region from a to b, a being the shortest or the smallest value on the x-axis, b being the largest, we end up with the integral from a to b. And then pi being the constant, I can pull it out. So I'll pull a pi out right here, and then f of x squared is our function that was squared, and then the delta x, remember, as we take the limit as delta x goes to 0, it becomes our differential dx. So this is where the formula comes from for the disk method. If you have the washer method, which is basically the disk method with a second function, like for instance if this had this is the square root function, say it also had the x squared function there. So when I spun this around, there would be this hole inside of all these. Then you would simply have a box here, and you would subtract out the area of the inner function. So that's, right now it's the disk method how we had it. If we wanted the washer method, we would take the inner function and we would subtract that. So this is the generic disk method or washer method, and this applies. The nice thing about this is the washer method works for both the problems that involve a washer, meaning two functions, an upper and a lower function, but it also works for the disk method if there's only one function. Because think about it, what would the equation of the lower function be if there was no lower function given? If there was only just the upper function, it'd be this line, the x-axis, which is the equation y equals 0. So y equals f of x, the upper function, y equals 0, the lower function. This would become 0, and it would just become the disk method. So the washer method is just a special case, or sorry, the disk method is a special case of the washer method when this lower function is equal to 0. Alright, but anyway, there's washer. You guys were deriving the disk, so you didn't have to have that g of x in there. I was just reminding you of that since there was that third function in here. So there's what it looked like if you answered this question, all these questions correctly. So the radius was given by the function itself. The width here was given by the dx, which is b minus a over n, the number of these rectangles that when they flip around the axis become these right circular cylinders. Alright, now let's move on to the shell method. So when we do these shells, again, our delta x is the width of these rectangles here, and now we're going around the axis that is perpendicular to the change that's causing these rectangles widths. So by that I mean we're moving left to right in the x direction to get these widths, and then we're revolving around the y-axis, and the y-axis is a vertical line which is perpendicular to this line. Before, when we did the disk method, we were revolving around the x-axis, and that's parallel to the change in x here. So we would be going around this way, or creating disk and or washers if there's a lower function. But now, since we're revolving around the axis that's perpendicular to this, or parallel to the functions, the height of these things itself, if you want to call it that, we get these washers, these cylindrical shells that surround and build up around each other, rather than it was up here where they stack up side by side by side. Now these things are going to build around one another. So this one's inside of this one, this shell would be inside of this one, and so on. Alright, now when you cut these shells and lay them out flat, you get a board, a rectangular solid, if you will, and we have 3 dimensions. We have our width, our length, and our height. So the volume of this thing would be length times width times height. So the H, the question mark in the yellow, would make this up. Alright, so what would give us these dimensions? What would give the dimensions of this board? Well, the H, the height, that's the easy one here. H is given by, if I'm looking at this one right here going around, H is given by the function itself. So this time, instead of H being the delta x, this time H is given by the function. So H is f of x this time. The question mark here, that's the little tiny gap at the bottom of these things. Well, that's going to be given by our delta x. Alright, and then the yellow part, that was supposed to be the toughest part of this one. The yellow part is the circumference of this circle, and circumference is equal to 2 pi r. Alright, if you remember that formula for circumference, 2 pi times the radius. And then what's given us the radius? Well, again, this would be like the circumference going around the top here. The radius is from the y-axis out to where, whichever one of these we're rotating. And if you look at that, this is simply just the x-axis. So r in this case, the radius is just x. Alright, so this guy right here is 2 pi times the x coordinate wherever we were. Alright, so we get h is f of x, and then this is delta x. So the formula for one of these is 2 pi x times f of x times delta x. So length times width times height. Alright, and then when we integrate this, do just like we did before. I'll pull the 2 pi out, the constants. We'll go from a to b, wherever we're starting to where we're stopping. And then as we take the limit as n goes to infinity or delta x goes to 0 with these, we get the differential. And now we have x f of x and then the 2 pi out here. Okay, so there's where these two crazy looking formulas come from. They seem strange because we're squaring a function and we're not squaring a function and pi is involved. But when you actually see what it is we're doing, when you see the geometry of it, the visualization of it, they make very good sense, where these things come from. Circumference, 2 pi r, height, f of x, width, the dx, and then here, pi r squared h, because it's the right circular cylinder when we do these revolutions around an axis, these rectangles with width delta x. So it becomes this when we take the integral. Alright, so I hope that makes sense. If not, just send me an email or come by my office and we'll discuss it. But I do want you to understand where formulas come from, not just memorize them.